but I think what's very interesting, there's a lot of open questions. I think a lot of lightning observations to remain to be done. We really don't know where the TGF is located in the thunderstorm. We have only 1 or 2 observations that are starting to give us a clue about that. We don't know what triggers a TGF, what makes a TGF happen. There's observations of gamma rays from the ground that last for many minutes. And then we seem to have a similar spectrum from this relativistic runaway avalanche process. So why does that process sometimes make emission that lasts for minutes, and sometimes it makes emission that lasts for tens or hundreds of microseconds? It's just, why are the timescales so radically different? That may be related to this triggering question. Maybe sometimes if you don't get the trigger, it lasts for minutes. So there's just very fundamental questions, I think, that call out for more observations. And finally, if you want to read some of our papers about this subject, that's the link to it. So, ready for questions?
Thank you for a nice talk. It is open to discussion and comments. Do you have any question?
I have a question about the comparison between TGF and Warren data. Could you tell me about the spatial relationship?
The spatial?
Relationship. You show the temporal relationship. I want to know the criteria of the comparison between the Warren location and the TGF location.
What we do is we take the Wolin data and we look for any discharges within, I think, 1,000 kilometers, and I think it's a 10 millisecond window, and we consider anything found in that window to be an association, and it turns out that what we find is the associations are within 300 kilometers and tens of microseconds. Once a small fraction of them turn out to be several milliseconds. That would be the case in the last slide I showed that there were actually multiple fast processes. I think occasionally we miss the one that's right on the TGF and find one that's a couple milliseconds away. But about 95% of the time we find it be within tens of microseconds. So we use this large window, and then we find that it's actually very close. And we've done control times where we pick we pick a time nearby to the TGF and try to find a match. And we take an offset time and say, okay, can we find a match under the same rules? We don't find matches except maybe 1 out of 1,000 or 1 out of 10,000 times. So we have good reason to believe that these matches are not by chance. And so, this example shows you, I think you asked specifically about the spatial matches. The blue squares are the spatial matches. They match it's the same, this is the same, this is the discharge showing you the matching time, and then when I show it in position, I don't know if it's exactly the same TGF because I showed you on the figure, but if we had the same figure, it would have that kind of time match, and then this is the position match, this blue square. So we have thousands of, this is plus, I think this is plus and minus 5 seconds or plus and minus 10 seconds. We have thousands of lightning discharges, and the one that landed within tens of microseconds is this blue square there and this blue square here, and this, I think this blue right here is a lake. They don't, I think this is actually purple and this is blue. It doesn't look very different on this screen. So, does that answer your question?
Yes, thank you very much. And how large is the field of view of the sensor?
The sensor, with TGFs, the gamma rays go up to 30 MeV, and they're even able to go through the Fermi spacecraft. We basically see in all directions. And the horizon is about 2,000 kilometers away. The Earth extends less than half the sky. It's about 1/3 of the sky, and that's about a little bit more than 2,000 kilometers away.
Thank you very much.
What do you say about the field of view 30 degrees or so?
That is our estimate of the beam size that's intense enough for us to detect the TGFs. That's based upon the fact that the location that we find, this is the source location basically, and this is where the spacecraft was. And so for the spacecraft to be, we're always finding for these bright TGFs that the source location is within this red circle, which is a 300-kilometer radius. So the sub-spacecraft location is here, say, and the source is within this distance, and the spacecraft is up here. So if this is the maximum distance, this gives you the angle. So the beam, this is the maximum beam angle is this angle, which is approximately 300 kilometers this way and 500 kilometers up is the maximum beam angle, which is about 30 degrees.
Thank you. Any other question?
Thank you. You talked about some TGFs appear before lightning, detected by the volume. Because I guess the volume won't mainly detect stronger return strokes. So is it possible that before the lightning there are some other discharge processes that is undetected? So it makes TGF appear before lightning.
That's possible. There could be processes, weaker processes that Woolen is not able to detect. These are probably, in fact, that we're detecting 30% of the TGFs are associated with Woolen is also saying that they're stronger than average processes. The detection efficiency of Woolen is usually cited as being 10%. And the fact that we're able to match 30% of the TGFs to Woolen are saying that these are stronger than average discharges, which are probably higher current than typical lightning discharges. So there could be in the sequence of the processes, there could be a weaker one before, which is actually the one that triggers the TGF. That Woolen is not detecting. I think the answer to your question is possibly yes.
So currently there's no way to determine which becomes
Well,
first.
I think there's a way. We need to do observations with better detectors and closer, and so some people are starting this, and like Steve Kummer is doing this from southern Florida, and I urge other lightning observers to join with us and to try to do these kind of observations with their detectors.
Thank you.
Any other question? Thank you.